My name is Rasul Sorkabi from the University of Utah Energy and Geoscience Institute in Salt Lake City. Today is Friday, 20th November of 2020, and I'm privileged to introduce Mr. Sidney Green as our speaker for today's session. Now, Mr. Green, as most of you know, is a well-known personality and in Utah, and especially in the oil and gas industry. He holds degrees in engineering from Stanford University. He was the founder and past president of TerraTech, which was later bought by Schlumberger. So today it is part of Schlumberger. He is also a member of the U.S. National Academy of Engineering, a research professor at the University of Utah, and president of Enhanced Productions Company based in Salt Lake City. Now, the title of his presentation today is Technology for Unconventional Oil and Gas Recovery Required for Industry Economic Improvement. And his co-author for this presentation is Michael Ratner from Washington, D.C. He's also with us today. Thank you, Michael. Now, without further delay, I will hand over the session and the screen to Mr. Sidney Green to deliver his presentation, and I thank him very much for accepting the invitation to give this talk for us. Sid, please.
Thank you for the introduction. Dr. Sakari has a lofty goal for this forum, as he mentioned, including the Earth Science, Community Education, and so forth, remap. That's a worthy goal. There's a lot to talk about in this. This is the fourth in the series. Dr. Marjorie Chan from here at the University of Utah spoke first on geoconservation, preserving our heritage and opportunities for the future. And Dr. Mike Simmons and Andrew Davies of Halliburton spoke on October 21st on hydrocarbons, geoscience, and the energy transition. And Dr. Sharon Moses spoke on creating the geoscientist workforce of the future. Now, they were outstanding presentations, and so they set a very high bar for me to try to follow. I'll note I don't have any slides to show, and my comments today are available. If you email me, I can send them if you like, and I believe that this is being recorded, as Dr. Scotty mentioned, and that he will, I believe, make it available eventually. I'm going to speak about unconventional oil and gas recovery, most often referred to as shale oil and gas, and often by the layperson as just fracking. I would argue that over the past about 2 decades, shale oil and gas recovery requiring large-scale fracking has much affected the earth science community. I guess I could also say it's two-sided. Shale oil gas has much affected the earth science community, and the earth science community has much affected shale oil gas recovery. Let me go back again that the shale oil and gas really did create new opportunities for geoscientists, geoengineers. The rock was complicated. Depositional environment created vertical layering and resulting in vertical heterogeneity. And the diagenic transformation over millions of years led to horizontal heterogeneity, even within a given horizontal layer. And added to this, tectonic actions created fractures, faults, stress variations, and more. So this created a highly heterogeneous formation vertically and horizontally with complicated rock fabric, with discontinuities of layer interfaces, fractures, and inclusions, and overall extremely low permeability. Now, speaking of that extremely low permeability, my company many years ago, back in the 1970s, almost 50 years ago now, 45 years ago, was trying to measure gas permeability of some clay shales and clays that might serve as a cap for nuclear waste storage. And we concluded that the permeability was so low that we would just call it zero. But then in the late 90s and early 2000, producers came to me and began to ask, they would know, well, is the permeability a half a nanodarcy, or is it 10 nanodarcies, or is it 100 nanodarcies? They were trying to produce gas from these formations, and we could no longer simply consider the rock as having zero permeability. In the first decade of the shale development, primarily gas production occurred, and the earth science community learned a lot about the rock. Besides being very impermeable and highly heterogeneous, vertically and horizontally and stratigraphically complicated, we had to explain to the engineers that the formation wasn't just a layer cake structure of different depositional layers. For example, we found that conventional log analysis didn't work. Conventional log analysis found porosities, saturations, stiffnesses didn't fit the actual lab measurements. The log analysis had to be recalibrated for this new rock. And unfortunately, this was complicated because of the variability of these formations. It required a lot of core. In fact, I used to say that I felt I needed about 10,000 feet of core to really understand a given play. Those of us doing rock tests and core analysis had a difficult time convincing the industry that this rock was different. I was co-author on an early paper on shale gas recovery in 1999, where we argued that those that treat this unconventional formation as unconventional would do better than those that treat it as conventional. And we were indeed right. There was a lot happening in the earth sciences area in the first decade of shale development. In the second decade of shale development, industry learned how to recover liquids, including natural gas liquids, and moved to a more valuable product, oil. Interesting, in the second decade, engineers really led the way with industry advancing much more by trial and error. That's what George King called not too long ago the tried and proven technique of trial and error. Drilling and well construction overall made huge advancements. Drilling and well construction became a manufacturing process. In fact, wells and well completions, fracking got much bigger with longer laterals and pumping more sand. But overall, operational efficiency greatly increased, and the recovery environmental impacts also were reduced. Looking back, clearly the U.S. success at recovering oil and gas from these ultra-low permeability formations is remarkable, at least to me. It changed the U.S. and it has changed the world. Their science was a big contributor to this success. Now, several events happened during this 2-decade shale development period that have had a large impact on the earth science and engineering communities. Just as the industry was ramping up in the early to mid 2000s, the 2008 financial crisis occurred. This led to abrupt reductions in capital spending by the oil and gas industry. It led to layoffs, created much uncertainty for this relatively new activity. And of course, the first thing to go in economic uncertain times is research and long-range programs. A second event occurred in 2014, 2015 with an oversupply of oil and gas, and of gas too, which led to a large drop in oil prices. The industry again had to cut back, lay off employees, and again, the first to go was research and long-range projects. A third event, about a half-decade later, has been the COVID-19 world impact of 2020. This has come along with an oversupply of oil, a very abundant supply of gas, environmental objection to fossil fuels due to large carbon emissions, and simultaneously strong investment lending pressures on the industry for greater financial returns. And again, the first thing to go in 2020 was research and long-range projects. So one might look at the 2 decades of shale oil and gas development and think, wow, how could we have made so much progress through these difficult times? Well, huge technological breakthroughs were made, even in the face of such adverse conditions. I think one has to give the earth scientists and engineers much credit for their persistent contributions. Incidentally, I'll just note, current and historical oil prices were addressed in a very nice paper by Dr. Sakati in August of this year. It was entitled "The Oil Price Crash of 2020: Causes, Consequences, and Historical Context." Interesting observations were noted there.
Yeah.
And my co-author, Michael Ratner, who's online today, recently organized a U.S. Congressional Research Service seminar in Washington, D.C. titled U.S. Oil and Natural Gas Production, Ramifications for the U.S. of Volatile Oil and Natural Gas Prices. There's really much interest in oil and gas, and in fact, virtually every newspaper, every newscast almost will have something on energy related. I know the Wall Street Journal again this morning had an article from the London Energy Council, I think it is, noting how developing countries need hydrocarbon. Okay, this brings me to my topic, technology required for industry economic improvement. If one doubts that economic improvement is required, just consider the employee layoffs, bankruptcies, mergers and acquisition within the oil and gas industry that have occurred and are occurring every day. The industry is going through a great upheaval. Just as an example, Apple computers now, I believe, a little over 13 times the market capitalization of Exxon. You know, Exxon was the largest capitalized company in the world for not very long ago. Things have really changed. Investors and lenders have shifted the availability and deployment of capital greatly away from oil and gas. For both the producers and the service companies. Hydrocarbon consumers are being pressed to decarbonize, and the opportunity driver for the earth science community that grew rapidly in the early 2000s began to wane in 2015 and really dropped off in the spring of this year. To suggest that drastic technology change is required for shale oil gas recovery seems maybe an understatement in the face of all of these things that are happening today. The upheaval in the oil and gas industry is too great to think that the industry will recover in the sense of returning to an as-was condition. It has and will continue to change regarding the recovery of shale oil gas, in my opinion. It will not be recovering to an as-was condition. One might wonder, incidentally, in this change that's underway, could there be another big driver for developing for earth science? Maybe. I don't see large-scale economic improvement can occur other than through technological innovation. Let me diverge just a bit before getting back to directly to my topic and note a few things about the hydrocarbon industry in the future world energy mix. There's some very worthy comments that Michael Ratner, my co-author, made recently. We are in an energy transition. However, what the energy transition means, how long it will take to happen, and what it will cost is viewed differently by different individuals. Nevertheless, it is now being rapidly driven by money. It started with climate change and a large amount of carbon from burning fossil fuels, but now it is being driven much faster by the availability and deployment of capital. Money always has a big impact and is often the real driver, and that's the case here in my opinion. Fossil fuels, oil, gas, and coal provide about 84%, 2019, of the world's primary energy. 84% of the total world's primary energy is from oil, gas, and coal. Price availability and reliability drive the use. Oil, gas, and coal are cheap, available, and reliable, but they lead to large amounts of CO2 emissions. The new energy being adapted in the energy transition today is primarily solar and wind. Unfortunately, solar and wind are available intermittently, and large-scale and long-term non-fossil fuel storage is not yet available. This means on their own, solar and wind electricity are not necessarily cheap, available, nor reliable, if one really addresses other economic aspects besides just electric generation that's possible with solar and wind. At present, natural gas turbine peaking units are providing the fill-in when solar and wind are not available. Gas is at present really the storage vehicle that is allowing additional solar and wind grid electricity to be added. I note also regarding natural gas, it is already and is somewhat replacing coal in the US and even worldwide. This is lowering the US carbon emissions, and it's lowering world carbon emission growth. Natural gas is allowing solar and wind electricity and is lowering carbon emissions today. The second point by Michael Ratner is that it takes energy to produce energy. And it takes a lot of energy to support an energy transition, which is currently underway. Oil is primarily supplying the energy today required to allow the energy transition. And this was noted by the presentation by Dr. Simmons back in October in his second presentation series. He presented estimates by British Petroleum. And BP has been one of the most aggressive oil players to announce its move to lower carbon emissions and to diversify its business beyond fossil energy. BP numbers show that the energy transition is requiring more energy today to produce new energy in the future and may lead to an oil shortage in years ahead as the energy transition progresses. Literally, a high demand for oil is created as new energy sources are developed and built out. For example, a recent article in one of the major newspapers noted, if you like electric vehicles, if you like electric cars, you better like mining. It will take a lot of mining to provide the minerals required for the electric vehicles, for example. Now, based on public opinion polls, these facts are no doubt surprising to many, but they are facts. And a third point, Michael Ratner also noted that the oil gas industry is being driven by ESG, environmental, social, and governance issues. Again, capital availability for the oil and gas industry, among other things, is much driving ESG acceptance. Additionally, some of the stronger early supporters of ESG, like the large high-tech companies, are also driving ESG acceptance by the oil and gas industry, but in a complicated manner. These big high-tech companies are both consumers of oil and gas, and they provide services and products as clients to the oil and gas industry. It's complicated. As consumers of oil and gas, they require energy for their operations. Energy is required for the use of their products they sell, like cell phones, computers, cloud computing, data storage, and they require energy to obtain certain minerals and to provide hydrocarbons for plastics required to make the products they sell. They support ESG acceptance, but require abundant and reliable electricity at low cost. Sometimes abundant, reliable, and low-cost electricity requires trade-offs and compromises. Energy is complicated. Let me address more directly now my topic, technology for the oil and gas industry's economic improvement. The University of Utah conducted 2 National Science Foundation mini workshops on drastic change required for shale oil gas recovery. These were co-chaired by Dr. John McLennan from the University of Utah and myself. The NSF workshops addressed the potential of large technology change for shale oil gas recovery. As we considered technology at these workshops, we kept in mind that industry has made big improvements in efficiency of operations, really huge improvements. These improvements in efficiency have both significantly lowered the recovery cost and also have reduced oil gas recovery environmental impacts. These improvements have been accomplished by a strong industry focus on near-term, today lower costs, small step improvements assessed to a large extent by trial and error. The improvements have led to much increased efficiency, but unfortunately, the strong focus on near-term, today, lower costs has not allowed progressing toward a large change that appears to me to be big enough for the long term. That's the problem. Additionally, shale oil and gas production has been on a treadmill of sorts, with bigger wells developed with longer laterals and pumping more water and sand for hydraulic fracturing. But the wells continue rapid production declines. This requires drilling more wells to offset the rapid decline, and then drilling more wells and so forth. That's the treadmill that industry is on. As industry has much improved the operational efficiency, even though on this treadmill of operations, the recovery factor has not improved. That is, the recovered percent of oil and gas that is in place in a given play has not much increased. It remains low, maybe only 8% or 10% for oil and twice that for gas. Most of the oil and gas is left in place, even as industry drills up its most valuable, its very best properties. I'm not the only one saying this. Others with far more expertise than me are also noting that big change is needed. Banks and lenders have much been on this issue the past few years, noting that free cash flow from producer operations was too small to pay debt and make a profit for shale oil gas production. This caused the industry to first drastically squeeze the service companies for lower prices. It is the service companies that actually drill and fracture the wells. And then overall, the gas industry focused even more on near-term today cost reductions. The university earth science community that is all across the country noticed this in the form of reduced research support, former student layoffs, lack of new job opportunities, and enrollment declines. Nevertheless, the research community, the service companies, the producers continue to make improvements, small improvements, primarily in operational efficiency. We see continually what's called new technology, new things for the oil and gas industry being promoted. But unfortunately, far more is being spent on marketing than on actual technology development. Back to the NSF workshops. They include experts meeting and discussing this potential for large change, something of the scale of horizontal drilling and stage fracturing. Dr. Bruce Hamilton at the U.S. National Science Foundation supported our efforts via the University of Utah to bring together these researchers from universities, national labs, and industry to consider possible large-scale drastic change. The overall idea was to combine environmental and economic benefits in a win-win manner. The work concluded with the second workshop in February of 2020 this year, earlier this year, held at the Congressional Research Service in Washington, D.C. For reference, I think that final report of the workshop has been presented and is available. The NSF program quickly focused on three broad technology areas for potential large-scale drastic improvements. First, an alternative to augment or replace hydraulic fracturing. Second, how to increase the recovery factor. And third, how to manage production from lower quality reservoirs. In our deliberations, the program participants appreciated two key factors, two key things. First, there is no silver bullet, no simple easy fix to further greatly lower recovery costs and to lower the recovery environmental impacts. And second, that any large-scale change would likely be too big an effort for any one company, even the largest producers or the largest service companies. Any large-scale change would have to be a program calling on researchers at universities, national laboratories, and industry, and the combined efforts of producers and service companies. I'll comment on the potential technology opportunities that the workshops arrived at. Again, the three broad areas were first, to find an alternative for hydraulic fracturing to much increase the recovery factor and to properly manage lower quality oil gas reservoirs. Regarding hydraulic fracturing, a complete alternative to hydraulic fracturing doesn't seem to be on the horizon. Unconventional, ultra-low permeability formations, oil and gas recovery simply requires creating a huge connected fracture network leading to the wellbore. This is required in order to achieve economic oil or gas recovery. This is different from conventional oil production, where hydraulic fracturing is more an option to increase production. For unconventional shale formations, hydraulic fracturing is not an optional treatment, it is absolutely necessary. Current hydraulic fracturing has been highly perfected by industry. In fact, in my opinion, incredibly perfected. It is a highly efficient operation, but not so efficient considering the low oil gas recovery factor. Many researchers are currently working to better understand hydraulic fracturing, and hundreds of papers and presentations are made each year. The U.S. Department of Energy cooperative programs between industry and researchers are developing field real fracturing information. I would reference the NETL, National Energy Technology Laboratory, review of the DOE Unconventional Field Labs programs recently. It's a good review. These individual works and joint programs have been and are valuable and have helped the industry make improvements. However, they are not a focused program aimed for large, drastic change. They tend to be one-off programs without strong interaction among all the research efforts. Drilling the wells has advanced so much in the past decade, so that a concept of more drilling and less hydraulic fracturing seemed a direction to pursue. Dr. Mark Pearson, one of the participants at the workshop, was very helpful in showing this drilling, the great advancements in drilling. In fact, with regard to drilling improvements, it seems, at least to me, almost unbelievable that a 6,000 to 8,000 foot well, deep well, vertically depth, and a 10,000 foot lateral can be drilled in 10 or 15 days now. It's incredible, at least I think it is. More drilling potentially may be an augmentation to current hydraulic fracturing, but not a full replacement. This is particularly worth pursuing as a potential treatment to bring back life, maybe, for some of the several hundred thousands of low producing or even shut-in shale wells. The NSF program listed small hole drilling from the main lateral well and dynamic pulse gas fracturing as a potential for consideration. However, I note again, this would not completely replace hydraulic fracturing, but may augment and reduce the amount of hydraulic fracturing, as well as, in the first application, may well be a type of refracturing treatment. Small hole drilling from both vertical and lateral wells is not new and has been tried even recently. There was an NETL, again, National Energy Technology Laboratory, novel drilling review that came out late last year, if I recall correctly, that reviewed novel drilling, including small hole drilling. However, the small holes drilled alone from the lateral will not create enough new surface area to allow economic production. An energetic, dynamic fracture from the small hole could potentially create the required surface area. This too is not completely new. That is, a gas pulse may create fractures independent of the in situ stresses and the rock fabric. The stress loading with a sufficiently rapid rise time pulse can create a stress wave or a body wave into the near wellbore rock that will overcome or overpower the rock in situ stresses and the rock fabric. The pressure pulse magnitude must, of course, be great enough to create breakdown, thereby creating a fracture network around the wellbore. The initial near wellbore fracture network would need to be extended by additional pulses or injection, and proppant will be needed to maintain the created fracture conductivities. Being able to overcome the unfavorable in situ stresses, for example, maybe lower pore pressures due to already produced reservoir drawdown, or complicated rock fabric that would interfere with fracture growth, could give the possibility of a refracturing treatment and make it an attractive option. Regarding the second consideration from the NSF program, increasing the recovery factor, this could offer very large potential. If only 8 or 10% of the oil in place is currently being recovered, there is indeed plenty of oil in place yet to be considered. Doubling or even tripling the recovery factor would still leave most of the oil in place, but a doubling or tripling of the recovery factor for about the same drilling and fracturing effort would have a huge, huge effect on economics, on the recovery, environmental impacts, and on the known U.S. recoverable shale oil and gas. Increasing the recovery factor significantly would seem a must for improving the economic health of the oil gas industry. Subsequent to the NSF workshops, current market conditions have focused even more attention on increasing recovery factor. For the large-scale drilling and fracking currently undertaken, it is simply not acceptable to recover maybe only 8% of the oil in place. Dr. Mark Zobak at Stanford and others have drawn attention to geomechanical aspects of well production. Dr. Roberto Suarez Rivera at Van Gotten Laboratories and Dr. Ali Donashay and others have drawn attention to multi-well interactions during fracking and production. Dr. Dean Wilberg at Schlumberger and Ian Walton at the University of Utah and others have noted the potential impact of rapid early production on ultimate well life production. Clearly, for the relatively close well spacing, coupled with the large volumes of water and sand injected, and then followed by production of the reservoir, oil or gas, there are well-to-well interactions. Additionally, myself and others have argued that the complex nature of the reservoir fluid mobility is not well understood. To increase the recovery factor, fluid mobility away from the created fracture faces must be better understood and ultimately enhanced. The third of the NSF workshop's broad areas include managing lower quality reservoirs. Industry is rapidly drilling its best properties and will have to move to lower quality reservoirs, some suggest very soon. Industry and researchers made great progress in the first decade of shale development at understanding the shale rock, as I noted earlier. The second decade, however, has seen little advancement in understanding the rock. Instead, engineering efforts, accepted to a large extent by trial and error, tended to optimize the operation. And most recently, big data with artificial intelligence and machine learning is being applied by producers and service companies alike. This is good and is further improving efficiency of operations. But this unfortunately does not replace basic understandings. Big data tends to tell what works, not so much why it worked. More understanding of the rock and the fluids, and particularly the interaction between the rock and the fluid is needed to allow lower quality reservoir production without even larger hydraulic fracturing efforts. To deviate a bit, I don't know how many of you ever considered how many pounds of sand pumped is required for each barrel of new oil recovered. If 20 million pounds of sand is pumped in a single lateral well, which is not uncommon, and the well early production, say the average for the first 30 days is 44,000 barrels per day, that's 5,000 pounds of sand per 1 barrel of oil per day for new early oil production. 2.5 tons of sand to recover 1 barrel per day of new oil. To me, that's a lot of sand. To summarize the NSF workshops, they provided several generally accepted observations regarding the potential of large-scale change. And I might add that people might say, well, this is not rocket science. Well, you're right. After we put it in print, it's not rocket science. Say it is obvious. First thing is lower recovery costs and lower recovery environmental impacts can go together. And if they don't work together, one or the other will be a big loser, which will be a large negative. And right now, one of the big recovery environmental impacts has to do with the flaring and venting of methane into the atmosphere. The second thing, small hole drilling from the main lateral well and post-fluid fracturing looks interesting and could be an augmentation to the current large-scale hydraulic fracturing. 3, understanding the hydrocarbon fluid mobility for closely spaced wells and including some form of enhanced flow mechanism could potentially increase the recovery factor 2 or 3-fold. This would be huge. This is the biggest opportunity that we see, is increasing that recovery factor substantially. Next, better understanding of the subsurface rock and in situ stresses for shale reservoirs could avoid higher recovery costs and larger recovery environmental impacts per barrel of oil recovered for the lower quality reservoirs. Next, any large-scale change will not be easy and is likely to be too large an effort for any one company and will require the rallying of university, national laboratories, and industry researchers focused on a common goal of large change as opposed to one-off small step improvements. Finally, the government can be the catalyst to lead the way for a large-scale drastic change. To close, it is significant to note that in recent months, the requirement for a large-scale drastic change for shale oil gas recovery has certainly been highlighted. The impact of oil gas price volatility was the subject of Michael Radner's seminar at the Congressional Research Services in September. The shale oil gas industry has to be prepared for potential large oil gas price swings driven by supply and demand variability. And on top of this, public perception regarding hydraulic fracturing, now driven primarily by the desire to eliminate fossil fuels, does not seem to be tempered by the great importance to the U.S. of shale oil and gas. Hydraulic fracturing is a flashpoint for dispute, but it is absolutely required for shale oil gas recovery. Additionally, the service companies that drill the shale oil gas wells, do the hydraulic fracturing, and provide services for production have experienced large staff reductions and even bankruptcies in some cases. These service companies have been the world leaders for unconventional oil gas recovery, but they have been decimated by the changes in the oil gas industry overall. China and Russia are undoubtedly making great gains in technology relative to the U.S. technology, and this raises questions as to who will be the service technology leaders of the future. The U.S. has never been in a position of relying on service provider technology outside of the U.S. to drill, complete, and produce its oil and gas wells. This would be a big negative change. In conclusion, I want to speak just a little bit more directly to earth science and how my comments on shale oil gas relate to earth science. Certainly, recovery of oil gas from unconventional reservoirs has been a big driver for the earth science community, as I noted earlier in the presentation. That driver doesn't exist today. Where we are now regarding earth science is that earth scientists and earth engineers need to work together, in my opinion. For example, they need to work together to create large change that I speak of for the shale gas recovery, which requires both science and engineering. Additionally, other drivers are now at work affecting the earth science community. For example, the third decade of shale oil gas recovery is going to face headwinds from outside the technology, like capital availability, ESG issues that I spoke of, public perceptions, particularly hydraulic fracturing, and competition for energy markets. And this is a new one. It's no longer just oil, gas, and coal. Now it's oil, gas, coal, solar, and wind for electricity. To meet these challenges, earth scientists must be willing to move out of their comfort zone to work things new and different. The third lecture series speaker, Dr. Sherna Moser, spoke to teaching to conceptualize the problem. I often call this to develop a correct mental picture. We must not forget the old saying, there is no prize for correctly solving the wrong problem. It's difficult to solve the right problem if one doesn't have a good mental picture of what is the problem. The energy transition underway is in many ways without careful public weighing of significant facts. Daniel Yergin's new book, The New Map, speaks to how technological change takes time. It doesn't just happen overnight. Public perceptions, however, can change overnight and can be so wrong. I don't know how many of you remember, but King Hubbard's most famous presentation on peak oil was made here, right here at the University of Utah. It was in Kingsbury Hall in 1977, I believe. I was there, TV coverage chaired by Dr. Frank Press, the president of the National Academy of Science, when King Hubbard predicted that we would hit peak gas production in the mid-90s and peak oil shortly thereafter. How wrong those predictions were. Earth science related facts are so important after all. They are really environmental impacts that we are concerned about, generally related to the Earth, including our climate. They are Earth science issues. As for career opportunity in Earth science, individuals in their careers tend to move to senior positions, whether in research, marketing, management, and some move to executive positions. Earth science has been shown to be a good foundation for career progress. And in the years ahead, I believe it will be even more so, possibly. Thank you for listening. I'll try to answer any questions as time allows. And I know Michael Ratner is here too and online. And so he's also available for questions if there is time and questions. Thank you.
Thank you very much, Sid. Thank you, Michael, for sharing his ideas and insights.